The overall goal of this procedure is to classify enzyme hydrolyzable organic phosphorus in extracts of soil or manure samples. This is accomplished by first extracting samples with sodium hydroxide EDTA solution and adjusting the pH of the extracts. Then incubate these adjusted extracts with two different enzyme solutions on a 96-well plate. The final step is to measure enzyme-released orthophosphate using molybdenum blue colorimetry. Ultimately, most native orthophosphate, monoester phosphorus, and diester phosphorus forms can be classified in soil or manure samples based on the differential release of orthophosphate by the enzyme hydrolysis method.
This method can be performed inexpensively in any standard laboratory. The main advantage it has over existing methods like phosphorus-31 nuclear magnetic resonance spectroscopy is it can measure the potential for native soil enzymes to release orthophosphate from organic peat compounds in the future. Therefore, data obtained by this method can help forecast soil fertility or the potential for soil to release harmful amounts of algal available orthophosphate.
Add 30 milliliters of the 0.25 molar sodium hydroxide solution to 2 grams of wet or dried sample in a 50 milliliter conical tube. Incubate with agitation for 16 hours at room temperature. Centrifuge the samples 3000 times G for 30 minutes. Then transfer 100 microliters to a 1.5 milliliter microcentrifuge tube that already contains acetate buffer. The adjusted sample has a total volume of 1 milliliter and has a pH of 5.0. Prepare 2 stock solutions containing 0.5 units per milliliter of acid phosphatase in 10 milliliters of freshly prepared 0.1 molar sodium acetate pH 5. Now add reconstituted lyophilized nuclease NP1 from Penicillium citrinum into one of the 10 milliliter tubes of acid phosphatase stocks to a final concentration of 2.5 units NP1 per milliliter. Gently mix by inverting several times. Centrifuge the 2 enzyme solutions at 3000 times G for 30 minutes. In order to construct a calibration curve, begin by adding 1 milliliter of 1 millimolar potassium phosphate stock solution to a 1.5 milliliter centrifuge tube and perform 7 0.5 milliliter serial dilutions. Discard the first tube so that final dilutions range from 20 nanomoles to 0.625 nanomoles phosphorus. Now transfer the orthophosphate standards to the last 2 columns on the plate, beginning with 0 nanomoles orthophosphate in row A and ending with 20 nanomoles orthophosphate in row H. To the first 3 wells of column 10, add 40 microliters PP plus GP enzyme solution. To the next 3 wells of column 10, add 40 microliters PP plus GP plus NP1 enzyme solution. Finally, add 40 microliters of 100 millimolar acetate buffer to all 6 wells. Now each of the first 6 wells in column 10 should contain 80 microliters of solution. To the next 2 wells, add 40 microliters sodium acetate solution containing 10 nanomoles glucose 6-phosphate and 40 microliters PP plus GP enzyme solution. For each sample being tested, distribute 40 microliters of pH-adjusted sample extracts to wells 1 to 9 in up to 8 rows. After all samples have been distributed, use a multi-channel pipette to distribute PP plus GP enzyme solution to columns 1 to 3, PP plus GP plus NP1 to columns 4 to 6, and 0.1 molar sodium acetate buffer to columns 7 to 9. Perform this step rapidly to assure all samples get equivalent incubation time. Cover the 96-well plate with a lid and incubate samples, enzyme solutions, controls, and calibration curve exactly 1 hour at 37 degrees Celsius. In deionized water, prepare 50 milliliters of each of 4 stock solutions. Solution A must be prepared daily. Using a multi-channel pipette, rapidly add 25 microliters of SDS, 100 microliters of solution A, 20 microliters of solution B, and 50 microliters of solution C to all wells in the 96-well plate. Cover the plate and incubate for 30 minutes at room temperature. Finally, measure the absorbance at 850 nanometers in any tunable microplate reader. Using a spreadsheet application, first plot the inorganic phosphorus calibration curve with 0 to 20 nanomoles phosphorus on the x-axis and mean of duplicate absorbance measurements on the y-axis. Perform a linear regression and find the equation of the line of best fit. Next, calculate the background inorganic phosphorus by averaging the values in columns 1 to 3, and then applying the calibration curve to the data set. Next, to determine phosphorus derived from hydrolyzable phosphorus monoesters, average the triplicate sample values from columns 4 to 6 and subtract out control enzyme solution plus background inorganic phosphorus. Then, to calculate the phosphorus content from hydrolyzable phosphorus diesters, average the triplicate sample values from columns 7 to 9 and subtract control enzyme solution plus background inorganic phosphorus plus hydrolyzable monoester phosphorus from columns 4 to 6. A typical 96-well plate shows results for 8 samples and a calibration curve. Controls are in column 10. Color intensity increase between columns 1 to 3 and 4 to 6 is due to hydrolyzed monoester phosphorus compounds. Between columns 4 to 6 and 7 to 9 is due to hydrolyzed diester phosphorus compounds. Here, the method of high-throughput enzymatic hydrolysis was used to successfully analyze distribution of the phosphorus classes in a 0.25 molar sodium hydroxide, 0.05 molar EDTA extracts of a Vermont soil sample.
After watching this video, you should have a good understanding of how to measure native orthophosphate, monoester, and diester P compounds in soil or manure extracts using enzymatic hydrolysis. This technique may help pave the way for researchers in the fields of environmental chemistry and nutrient management to explore organic P behavior in soil or manure systems.